Hello! In a previous video, I investigated the implications of a flat Earth theory. This involved making calculations to show the implications of the theory, with the results being presented by way of graphs. Interpreting such graphs in reference to their meaning in reality can be an issue, so in this video I shall be showing some ways those results can be visualized. In doing this, a new conclusion, beyond those of the original video, emerges. To recap, the flat Earth theory I considered consisted of three hypotheses. The first, that there was a flat plane on which the mass of the Earth rested. The second, that there was a plane parallel to the flat Earth plane about which the Sun moved. The third was that the surface of a body of water is always parallel to the Earth plane. Let me also remind you of the warning I gave not to stare at the Sun. The first analysis involved predicting what a single observer would see if the Sun was indeed moving about a plane parallel to the flat Earth, as shown in this representation. Since the position of the Earth plane isn't identified in this theory, we can't know the distance to the Sun plane, labelled HFPS. We also don't know how far above the Earth plane the observer is. We do know that the Sun plane is a fixed distance above the observer, and we label this HS, which is perpendicular to the Sun plane. The distance to the Sun from the point of the HS vertical is labelled DS. We also noted that there are photons travelling in a straight line from the Sun to the observer, which gives rise to the observer seeing the Sun at a particular point in the sky. Finally, the diagram shows there is a horizontal eye line which is also parallel to the Sun plane. In analysing the triangle in this diagram, we used HS as the basic unit of distance and gave it a value 1. Values for DS were then calculated as multiples of HS. We then used these values to calculate some properties of the Sun as DS increased and plotted graphs showing these changes. Here we see three of these properties shown on a single graph. The blue line is the angle of the Sun above the horizontal eye line as it appears to the observer. This is a different but equivalent plot from the original video which plotted the angle theta, which increases with DS. The red line is the change in angular size as seen by the observer, but is scaled by 100 in order to be visible on this plot. Finally, there is the resulting brightness as perceived by the observer as the Sun moves further away along the Sun plane. How are we to interpret these graphs? Let's deal with brightness first. What this line shows is that the maximum brightness perceived by the observer is when the Sun is directly overhead, which is given the value 100. The graph represents the percentage value of the brightness of the Sun as DS gets bigger. Note the steep drop-off in brightness. By the time DS is 10 times HS, the brightness has dropped well into single digits. Turning our attention to the other two quantities, we see that the shape of the lines are the same, which means that as the Sun is observed closer to the horizontal eye line, then it is reduced in angular size by a similar proportion. In the previous video, we calculated that for the Sun to be 2 degrees above the horizontal eye line, DS had to be 27 times HS, and at that distance, the angular size is a tiny fraction of what it was observed overhead. Note that the values chosen for angular size give an initial value that is marginally bigger than the accepted angular size of the Sun as seen by observers on the ground. In order to get a better grasp of the meaning of these graphs, I'm going to present some direct representations of the properties and some comparisons that may be easier to visualize. Let's start by seeing how an object appears to move closer to the horizontal eye line as it is physically moved further away. To do this, I'm using the 3D image generator, Blender. This image shows two identical cubes. The cube on the left is placed such that the bottom is on the eye line of the observer. Note that we can only see the face of the cube that is towards the viewer. The second, identical cube is placed at the same y distance as the first cube, but is above the eye line. We can see the front face and also the underside of the cube because of how it is positioned. Using Blender, an image is generated when the right-hand cube is moved further away from the viewer. Here is what the viewer sees when the cube is twice as far away in the y direction. You can see that the whole cube is visible and its bottom edge appears to be about halfway down the stationary cube. At 5 times the distance, the cube appears closer still to the eye line and even closer at 10 times the distance. Also, we can see that the apparent size of the cube changes as it is moved further away. That brings us to try to visualize the changes of angular size of the Sun object. In the analysis, the size of the Sun was given as 1/100th that of the distance hs. That gave an initial angular size of about 0.57 degrees, which is marginally larger than the generally accepted angular size of the Sun. Consider this yellow ball, which has a diameter of 1 centimetre. So our analysis starts with this ball at a distance of 1 metre from the observer. If you think that this isn't representative of reality, consider that this ball is smaller than a UK 5p piece or a US dime. Next time you see a full moon, get one of these coins, close one eye, and hold the coin at arm's length, and you should find that you can easily obscure the moon from view. Note also that the analysis presented in these videos also apply to a moon moving about in a moon plane. Now, imagine being at a regulation-sized soccer pitch. If you squat down in the goal mouth, imagine what you could see if that ball, or a 5p piece, were placed 1/4 way down the pitch. That distance would still have the object 2 degrees up from the horizontal eye line. Halfway down the pitch is still more than 1 degree off your horizontal eye line. Let's move on to considering 2 observers who coordinate their observations of the Sun. In this case, the 2 observers see solar noon at the same instance and are also situated on the same body of water. Each month, the angle of the Sun above the horizontal at each location is given by these charts, designed to provide optimum angles for a solar panel. Let's use these values in our flat Earth theory to triangulate the position of the Sun each month. We start by invoking the water level hypothesis and select 2 points for each of the observers. Starting with December, we draw a line at the angle given, and the point at which they intersect is the place where the Sun should be at solar noon. According to the sun plane hypothesis, all subsequent triangulations of the position of the Sun should place it along this line. Now, let's use the January data to triangulate the solar noon position of the Sun for that month. We immediately see that this places the Sun off the sun plane we calculated from the December data. This falsifies the sun plane hypothesis immediately. If we insist the sun plane is a real thing, then we must contend with the idea that while we identified only a single sun in December, there are 2 suns when considering the January data, and each observer is seeing a different one. Alternatively, we can make the red lines intersect on the sun plane by moving Plymouth down below the water level, which therefore falsifies the water level hypothesis. As we apply the data from subsequent months, all these problems with the hypothesis are made worse. We have a choice to make, either to ditch the sun plane hypothesis or the water level hypothesis. Let's assume that it is the sun level hypothesis that is false and add a third observer with the same properties as the others. That is, they observe the Sun at solar noon at the same instance as the others, and they are situated on the edge of the same body of water as the others. We use the data from the original observers to triangulate a position for the Sun as before. We then use this Sun position and the third observer data to triangulate a position for the third observer on the water level line. Using the December data, the third observer is placed here. But using the January data, the third observer is in a different place on the water level line, and so it is with subsequent months. In order for the water level hypothesis to be true, Malaga must move away from Abidjan in the months from December to June. If we look at the trajectory of the triangulation lines for the third observer, we see that, although they intersect the water level line in different places, they look like they might actually converge at a single point below the water level line. That is indeed the case. That means that we can position 3 observers in this diagram such that the angle data in each case is correct, but that means one of those is definitely not on the water level line, which falsifies the water level hypothesis. What are we to conclude from these visualizations of the data? For a single observer, we saw that the model predicted properties of the Sun that are just not observed in reality. In order for the sun plane hypothesis to be correct, the sun would have to dwindle to a point in order to get close to the horizontal eye line, and it would have dimmed to a fraction of a percent of its maximum brightness at the same time. Not presented here, but in the previous video, we saw that the sun would have to be 2 to 3 times further away again in order to appear due east in Greenland at the equinoxes. Also, this model does not predict the sun ever appearing below the horizontal eye line, which it does consistently in many places on the planet every day. All of that is rendered moot by the results from 2 observers. In that analysis, the sun plane was false, or there had to be multiple suns, or the water level hypothesis was false. Discarding the sun plane hypothesis seemed to be the minimum required to have results that were consistent with the reality for the 2 observers. Having discarded the sun plane hypothesis, we added a 3rd observer, but in order for that to hold true, Malaga had to physically move about on the water level plane each month. However, we did find a point for Malaga in which the angles of all 3 observers could triangulate a single sun, but that placed one of them below the water level line, thus falsifying the water level hypothesis. So, where does that leave this flat Earth theory? From one observer, the notion of a sun plane seemed to be highly unlikely, and using 2 observers, the sun plane hypothesis came up false. When 3 observers tried to make their observations consistent with each other, we found that the water level hypothesis must also be false. Where does that leave the remaining hypothesis? It seems highly unlikely that hypothesis is true, but if it is, different hypotheses about the sun movement and the behaviour of water must be found and tested. Thank you for watching. If you have any comments, questions or corrections, please put them in the comments section.